All right, so this is our 29th SLiTHEr. It's the last one of 2021, and we are going to be talking about getting into computational chemistry and inorganic chemistry. We're in good hands. We have Kyle Grice, Lori Watson, and Adam Johnson here to tell us about how they did it and how we can too.
All right. Thank you. So I'm going to be the lead off, and then I'll quickly transfer it over to Lori and Adam, and then we'll have plenty of time for discussion. Just a reminder that you can find all the other SLiTHERs on our collection on Viper. So this is our 29th. We have 28 other ones you can check out. So we're all experimentalists by training. So this is kind of how we got into it. So I'm going to quickly tell my story, and then we'll move on. So I didn't do any computational chemistry in graduate school or collaborate or anything like that. And so I was just experimentalist. My postdoc started dabbling. We had ADF, which is one of these commercial systems. And I played a little bit, but didn't really get into it. And I would collaborate with computational chemists. But since being at DePaul, which is where I am now, as an assistant and associate professor now, we had Gaussian, and we have a computational person. And so we had a bunch of space to do calculations. And so I started learning. And so I chat with my previous collaborator, John Keith, who's now at the University of Pittsburgh. He's a computational chemist. Whenever I run into problems, or my computational colleague, and get set up. And the trick is that anybody can do this and get involved. And so I'm hoping that today we can the three of us can show you some of the things that we've done, and we can all talk about it and things. The main thing is just like all research, is take baby steps, and then let your experience evolve, like make mistakes, read up on things. The great thing about computational chemistry is you can't really break glassware, and you can only break the servers if you try really hard. And so, things change. So for example, I used to do certain types of DFT with these alphabet soup thing, and then I changed to a different alphabet soup based on reading papers. So just some things to think about is that whatever you're doing, there's lots of literature out there. Read up on your approaches, and use approaches that have been appropriate for inorganic chemistry. And so I think as inorganic chemists, we use metals. So one thing I just want to say up front is that most of the stuff we're talking about is DFT. And so there are some, lower, quote unquote, lower level models like semi-empirical or force field models, like stuff for docking and things like that. Those are generally not good for metals. And so, be sure that what you're doing is something that would be reasonable for what you're trying to do. And you have some reason to use that approach. And then another thing is figure out what can you do. And so again, this takes playing around. So start small molecules first and see how long things take, see what comes out. Just a note again about kind of the general approach for DFT is that the more electrons you have, the longer it takes, but it doesn't scale linearly. It gets longer and longer the more electrons you add. So it might be worth trimming down the fluff and just starting with a small molecule as you're starting to play around with DFT. And then there's other things you can add like solvation and stuff. Do you really need it if you're just getting into teaching or using it? And so you can kind of build those things on top as you go. And then as you learn things, you can learn other new tricks and tools and get into them. Like NVO is something that I'm learning now, and it's really cool. It basically allows you to see things like hybridization in molecules. And there's some interesting references in our previous SLiTHERs talk that was on this paper here from Chem Ed by Ulrich Feckel. And he gave a great talk on how he taught it in a lecture, but there's some great references about the computational kind of stuff behind what he talked about in his SLiTHER. So that stuff's called NBO, and I'm happy to chat more about that later. And again, it's okay if things crash. A lot of computational chemistry is, oh, that crashed. Why did it crash? What did I do wrong? And then you just say, okay, well, maybe I typed in this thing wrong, or maybe something, and then looking at errors and talking to your colleagues. And that's how research goes too. So that's just some kind of broad overview. I just want to show you an example of something that I did after I've learned a while. This is not my first computational paper, but one of the things you realize is that accuracy is relative, right? And that so some levels you can get like some relative information, but if you want it to be like quote unquote accurate, you need to think about it some more. So for example, if you have a crystal structure of something, you can benchmark the structure versus the crystal structure. If you're trying to look at IR or Raman data, every single computational system is inaccurate by definition. And so you can get relative numbers, which are great for teaching and stuff, but if you want accurate numbers, you need to scale it. And one of the best ways is to plot your calculated data versus your literature data, and then get a scaling factor that way. And every different approach has its own scaling factor. And so this is an example of what I did. Sherry Lentz is the PI on this paper, also at a primarily undergraduate institution, inorganic chemist. And then I did some DFT, all the DFT in this paper, and I had students who did some experimental work for Sherry as well. But what I was calculating was pKa's, which you can calculate in acetonitrile. And so what I did is I went in the literature, found all the known values for these are a bunch of common known simple acids like pyridinium, aniline, acetic acid, benzoic acid, imidazolium, and they have known pKa's. And so then I would calculate the pKa's, which you can get from a delta G, right? And then compare them versus the literature values. And so if you plot the DFT calculated pKa versus the literature value, it's pretty linear, but it's not like, but it's its own relationship, right? And so then what you can do is say, okay, that looks pretty good. Is that good enough for me? Sure, right? It depends on how good it is. So it turned out that the average unsigned error was about 1.4 pKa units, and then the worst was 3 pKa units off. So I was like, okay, I can trust this within plus or minus 3 pKa units. And then I used that equation to try to find a pKa of a metal complex that we were interested in, for example. So accuracy is something that you should assume going in. You're not going to get accurate values unless you benchmark them somehow. But relative can be fine for teaching. So that's really kind of the introduction that I wanted to give before I pass it off to Lori and Adam to talk about some of the stuff that they've done in teaching and research in computational chemistry as well. And we'll have time for discussion after our short presentations. So I'm going to pass it off to Lori now. I'll stop my sharing.
All right, thank you very much. Let's see if I can't share my screen here. And might even put it on slideshow. All right, can you guys see that?
I see loading. There it is. Viper intros.
Excellent. Excellent. So as Kyle said, I'm going to mostly talk about how I use computational chemistry in my inorganic chemistry class. When I was in grad school, I was sort of mostly a synthetic organometallic chemist, but I did quite a lot of DFT calculations too. And so when I, became a faculty member, that was always going to be part of my research. But I wasn't sure how it was going to fit into teaching, because at the time, what I knew was sort of command line interface, VI editor kinds of stuff. And that's a pretty big ask to teach students. And so I'll talk a little bit about what I did for that and what I'm doing now. So at Earlham, we do computational chemistry in our honors level Gen Chem lab, just a little bit. And then I teach the PChem sequence and inorganic chemistry. And so my students see it in both of those sequences. But students sometimes take inorganic chemistry before they've had PChem. And so I often do kind of an intro to what computational chemistry is for them. And I just pulled a few links from Viper of a various number of sort of 5 slides about that give you some intro to what computational chemistry is. So if you've never done it at all and just kind of seen it in some papers, or if your students have not seen it, some of these are really good examples of how to kind of quickly get your students to just sort of understand what it is without a lot of the technical bits. And there's lots of technical bits. And especially if you're teaching a PChem course, that's probably, really great to go into in different types of methods and when you use what and what they all do. And that's all great. For an inorganic class, I want to focus on helping them use calculations to illustrate some principle or some topic we're discussing in class. So the focus is less the calculations and more the learning about whatever theory. So there are those 5 slides about on Viper. So at Earlham, I use Gaussian as the computational engine, but I use a program called Webmo as a graphical user interface to Gaussian. And this has really made it able to be used for me in classes, because it really is no harder for students than drawing something in ChemDraw and selecting options from a drop-down menu. So it's really easy to get students to use it. There are other programs that will do some of the same things. I mentioned GaussView, but WebMO has the advantage of being able to hook into a variety of computational packages, including ones that are free. Okay, so Gaussian is not free, but there are programs out there that'll do a lot of the same things that I'll be showing you and that Adam will be showing you. And so if you're at a school where you don't have a lot of resources to purchase things, this can be a good thing. So WebMO has a free version, though they also have some versions if you're supporting a lot of users that you pay for, but it's pretty low cost compared to some other things. So that's what I use. Gaussian is nice just because that's one of the computational packages that you'll see researchers use, right? And so if your students are going to use this later on in graduate school or want to learn about this field of chemistry, it's nice if they're able to use something they might use in the future. All right, so I start out using doing a computational experiment for my first lab. And so this will be, we usually start class on a Wednesday and this will be the Monday after. So they've learned nothing inorganic chemistry wise at this point. We're still sort of reviewing some of our Gen Chem that they've had a couple years ago and starting to sort of push at the edges of it, right? And so the first experiment, computational experiment I have them do is using WebMO and Gaussian to calculate the complex between ammonia and BF3, right? So, and look at calculating geometries of them, having them, try to remember some of their VSEPR theories so they can explain and rationalize some of the bond lengths and bond angles in both ammonia and BF3, and then the complex, look at atomic charges on these. I have them calculate the molecular orbitals of each of them, and then the complex is sort of a reminder of some baby MO theory that they might have seen in Gen Chem, and as a preview of actually deriving molecular orbitals, which we'll do in about a week from when I usually do this. In this 3-hour lab, I usually spend about the first 15 to 20 minutes describing what computational chemistry is, using one of the 5 slides about that I showed you earlier. And then we get right into it. We all calculate usually methane or something together, but it's really pretty intuitive, the WebMO interface. And so it's pretty, they're ready to kind of go real quick. And then I circulate and, they do click things wrong, or they don't select optimize, plus vibrational frequencies, which is one of the job types. They just do a single point, which isn't what I asked for. So, there's places where I'm actually useful, but so we practice calculating some pretty easy calculations, and these are really, really quick. We have a cluster at Earlham. You, I think, could even calculate. WebMO has a demo server. These are fast enough you could actually do on the demo server. Some of the transition metal ones are not, but this, if you want to try it out, you can use the WebMO demo server and see what it looks like. So these are pretty fast. So we do that, and then we usually do one more something. So sometimes I do a periodic trends activity that's actually on the WebMO site. They have some example educational kind of learning objects on there. Sometimes We've talked about hypervalent compounds. And so I have them calculate that and try to answer the question, are there really 6 bonds in SF6? And what does that mean? How many electrons might be there? You could use NBO that Kyle talked about. This would be a kind of interesting place to use that if you wanted here. So it really is just sort of an intro to computational chemistry and using the program, but I am illustrating some of the VSEPR things and some of the molecular orbital stuff that they would have seen in Gen Chem and that we're going to be talking more about in inorganic. The next time my students see it a lot is when we're starting to look at coordination complexes of transition metals and organometallic complexes, right? So we do a second kind of larger sort of experiment. And we do this actually in class, sort of pieces of it in class and as a sort of problem set, because they already now know how to use the program. To look at back bonding of carbonyls, right? And roles of metals and oxidation states and trans, the ligand trans to the CO. And I have them make predictions, you know, when we look at some literature and like, okay, now how could we calculate it? What might you expect to see? And so I usually do something pretty similar to the learning object I posted on Viper a while ago. And that's the using computational chemistry to discuss back bonding. So these complexes are larger. Okay, so you probably would want to use a cluster for these if you have one. Sometimes your computer science department will have one if you in chemistry don't, and they'll be happy to load up computational software for you. And like I said, there are packages that are free, so it doesn't have to be Gaussian. But we do some looking at different metals. We do some looking at trans effects. We see whether the predictions that we've made or that we've looked at in papers are true or not. And we do that kind of part sort of together and in small groups. And then usually as a sort of problem set activity, I give them the great back donation challenge. And students often really get into this. So we've been talking at this point about ligands, lots of different kinds of ligands, you know, acid base, oxidation state, all the good stuff, electron counting. And so their challenge is to find the ligand that would give the highest or lowest, you know, whatever CO stretch trans to it. And so they have to pick the metal, they have to pick oxidation state, they have to pick the ligand, and then they calculate it, right? I make some guardrails so that it doesn't take forever, right? So third row transition metals, for example, are faster to calculate. So we do that. I give them a pretty simple method and basis set that's pretty fast, not going to be as accurate as you know, Kyle's new favorite one. But for teaching and for this, it gets them a decent answer. But of course, the most important piece is thinking about what their strategy was, right? It's the thinking of like, well, what do I predict to happen, right? Because then they're trying to synthesize a lot of the things we've talked about in class and using the computation to kind of confirm or not their answer. So I've done this for a number of years, and it's usually fun. Sometimes they come up with really interesting ligands that I kind of need to ask my organic colleagues, like, could we make that? And by we, I mean, like, if it's not an Aldridge and there's not a prep I can Google on, it's not my thing. So sometimes I have them talk to a colleague to make sure it's a real ligand. But often they come up with some good ones. I've done other things in inorganic chemistry too. One of the things I often do is, depending on what synthesis labs we're doing, we'll use computational chemistry to look at something about those. So sometimes it's just calculating the structure. Sometimes it's trying to calculate the IR or UV vis or NMR spectra. There are some issues with trying to reproduce experimental data, and Kyle mentioned a couple of them. So this is a good opportunity to talk with students about the fact that just because you can select an option from a drop-down menu doesn't mean it actually gives you the answer that you expect, right? That computational chemists spend a lot of time thinking about exactly what methods and what scaling factors and, you know, how to make it work. So it's often a good conversation. There are ways you can calculate, molecular orbital energies. There's a lot of things you can do. There's a number of labs on Viper, a couple of which I've used, or I've used things similar with labs I do. But these links of ones on Viper are ones that combine both the computational and the synthetic aspect. And so that's really nice for students, because many of the papers that you guys have seen, I mean, it's sometimes hard to find a paper now that's purely synthesis, right? A lot of inorganic papers will have a computational component. And so it's nice for them to see that it can work with their lab experiments too, and really kind of work synergistically. So those are just some examples. I think Adam's got another one that he's gonna kind of share. But that's some of the things I do for inorganic chemistry. So it's fun.
I decided, I quickly wrote my background listening to Kyle talk about his background. So I also did not do really very much computational chemistry as an undergrad in grad school or as a postdoc, although I actually did a little bit. I remember trying to draw a buckyball in the early 90s on some, I don't remember, it was pre-Linux. It was one of these boxes that you could get. I can't remember what they were. Like, they're super high-end computers, and like this, the thing would crash just trying to draw the stupid molecule, right? And then in grad school, I did a little bit of computational chemistry, but it was like extended Huckel level of theory, and I learned how to use this DOS program to do that kind of stuff. And then we collaborated with people when we had real computational problems. And then at Harvey Mudd, I had the fortune of having a really good computational colleague, and we worked together over the years and failed to publish any of that work. So that's sort of what I did. I have mostly used computational chemistry in teaching, although I think I just remembered that we had this weird X-ray structure, and I didn't believe it because it was a tautomer of what I thought it was. And so I did the calcs. And it was like, yeah, the tautomer is actually lower energy than what we thought we had. So that was kind of neat. It's a little throwaway line in a paper that, just sort of talks about a ligand. So, I like using computational chemistry to sort of show, a little bit more. But I've mostly used it in teaching. And if I could figure out this computer. All right. So we do computational chemistry in the first year curriculum. And last year especially, we were 100% virtual, and so we did some computational work on the in-between weeks when we were supposedly doing synthesis, which was watching me make molecules on a video. And so this is like a 20-page long document, but I sort of extracted some of the details here. So, this is a calculation on a single atom, and they did neon and then neon cation, and they saw which one was higher or lower in energy. And then the ionization potential of neon is known, and so we can compare it to the experiment. It was within 1% at whatever level of theory we did. And then we did the same thing for the bond association for HCl. And this was, again, very close to, 1% error. So, we're showing the students that you can actually do this and get really good values. And then in week 5 of the course, we make vanillin derivatives in class. And then a couple years ago, my colleague Kathy made a little worksheet on this, and then we did it last fall. And so what they do is they calculate sort of simple structures, methane, methyl bromide, methyl chloride, formaldehyde, alcohols, and they measure the stretching frequency of CH bond, CO bond, OH, and then they compare it to vanillin, which has all of these functional groups. And the idea is you're trying to see that, the reason why we do functional groups in organic chemistry is because the CO single bond stretch, it moves around a little bit, but it's about 1,000 to 1,300. The CH stretches are consistent. The C double bond O stretches, so the students can see, oh, that's why we have these tables of stretching frequencies in our books that we can then use to identify compounds. So, we don't do all the functional groups in our Frosch Chem course, but we do a couple, and this is a good way to sort of solidify that knowledge for the students and show them. And this is actually a student data table from their lab report. It was so well done that I copied it. Like, I don't even need to do this now, and the student did it for me. And then we actually calculated NMR, which you can do now. You can calculate UV-Vis and NMR. And I should say, we also use Webmo interface to Gaussian. We have a local cluster. And so this is just the 60 megahertz spectrum of vanillin that the students take. And then this is the calculated structure. It's actually really close. You got the aldehyde, the methyl group. It's only off, by half a ppm. Got some aromatic stuff here. And then we talk about how this OH peak, which can move all over the place depending on solvent, hydration of the solvent. So, the students are pretty impressed that it comes out this good. And then if you actually add line shape to this, instead of it just being a single point, then it really starts to look like the real spectrum. So that's a new thing that I hadn't done before. It does a pretty good job with simple molecules. It does not do a good job with organometallics. And then that's sort of what we do in the freshman course. And then in Chem 104, which is my weird foundation level advanced inorganic chemistry course, that is the first course in the major, and they've all taken PChem and quantum and physics and all this, so it's a junior level course. So I have started trying to do more calculations in that class. What I've learned, and actually looking at your thing that you showed, Lori, which I totally want to adapt and implement, I want to start with some more simple Vesper type calculations and show the students that, and I have not given them enough time. 2020, that was the year I was going to really give computational chemistry the time, and I can't remember what happened in March of 2020 that disrupted my plans, but something must have happened because I did not do it. So maybe this year I'll end up doing it in the spring. So here I had them calculate water and a PF6. And, I give them some pretty detailed instructions. They've all seen, most of them have seen some of these things before, either in the freshman course or somewhere else. So it's not totally new for them. I do this sort of as a homework assignment. I show them briefly in class, and I usually do some office hours, and they can calculate some things there and get the structure and the geometry. And then later I have them do ClF3 and a titanium hexafluoride, just to see a transition metal compound with an octahedral geometry, and have them sort of describe the HOMO-LUMO, the stretching frequencies, the MOs. And so I have them compare the way I think about these MOs is I teach a very sort of back of the envelope graphical MO theory, and then I say, well, then you want to go look at the real calculations to see what the MOs actually look like. And can you extract your MO that you calculate out of the mishmash of all the computation? And in order to really see what's going on, you've got to draw a picture of it on the back of a napkin or something like that, because it's really hard to see what's going on. And so this is just a lot of words, but I have the students calculate MO energies, HOMO-LUMO gap, things like that. And then in the laboratory, and this is actually an addition that I've been doing for a long time, and I think I only posted it during COVID, but I have them calculate the CO stretching frequencies of a series of manganese compounds with different geometries here, and they can actually determine which one is the lowest energy compound during the series, and why when you oxidize it, it does a change in geometry. And I talk about this is more energy, but I talk about the stretching frequencies, like you said, Kyle. You have to scale it to some sort of scaling factor. And the main thing I like to do with this is to more easily show the students that the sort of the trends that you were talking about, Lori. We make a series of group 6 arene tricarbonyl compounds with, and I've always wanted to have a whole series of these, and these are all known in the literature, but the IR stretching frequencies change so much depending on the technique. So the paper that I have has like 50 or 60 of these stretching frequencies, but they're all done in a Nugel mol. And the way we do it is in the solid state with a diamond anvil ITR, and we get totally different numbers. And so you can't compare them. And so and we can't make some of these molecules. So we do it in the computer, and we make different molecules and see which one has the highest or lowest electron withdrawing ligand or whatever like that. So that's sort of how I use it. It's my last slide. So that's how I use it. And like I said, I try to show them more. Where'd you go? More how to use the results rather than the theory. I'm not a theorist, I'm not going to teach theory, but can we use these results and actually get something? And so we talk about benchmarking, and we talk about scaling factors and that kind of stuff. And the students generally like it. I have struggled with how to really evaluate it, because sometimes the students can have technical issues, or they can't log into the stupid cluster. And, you know, those are things that have inhibited my ability to be really good with this. But the main thing is I haven't given it enough time. And so I think starting small, I don't know that I need to go all the way back to neon and neon cation, but starting with sort of some simple Vesper structures. I like the borane ammonia complex. It's a great one to try. And then build to an octahedral complex, and then see where you go from there. So that's sort of oh, it was a Silicon Graphics workstation. I finally saw the chat. So yeah, that's what I was working on as an undergrad. So yeah, that's basically what I have, and I think we're basically done.
Yeah.
Great.
So I think
Yeah, thanks for the three of you for telling us about what you've been up to. I'm sure there's lots of people that have comments or things they've tried or questions for you. We'll open up for discussion.
If I wanted to add that also on the Viper website, I got permission from the Shodor people and the folks that teach a lot of computational chemistry to take some of their activities, and I updated them, and they're basically activities for teaching what can you do with computational chemistry. So not necessarily inorganic, but what's a basis set, and you know, how do you minimize an energy, and then getting into spectroscopy and those kinds of things. So I have a collection on the Viper website that I worked all of those so that they can work in WebMO. And then I also have answers from when I did I tried it all out and put answers as well. So there are answer keys, which is really, really nice to have. So there's a series of activities that I made into a collection on Viper. Also, I think one of the last ones does NMR, a little bit of NMR, and the WebMO interface with its most recent version, or two most recent versions, whatever, is a million times better with NMR than what the older versions are. It can do some really cool things now. So that activity that I have in there needs to be updated to go with the new WebMO.
Great.
The thing I found about NMR, it was a little, I agree the WebMO interface was great, but it calculates just sort of the chemical shifts based on the shieldings, but it's set to some random arbitrary 0 point, whereas we've set it to TMS, right? And so you have to tell the computer where TMS is. And so what I normally do is I find an aldehyde peak and set that to 10, and that's a little bit easier. And then it's like backwards, like you'd think you'd have to, I need to subtract 70, but it's actually you have to add 70, but it's pretty easy to figure out.
Yeah, I mean, it used to, if you just go straight into Gaussian, what you get is a chemical shift. Gaussian is a static structure. So you get a chemical shift for every single proton in your molecule. And whereas WebMO now has gotten smarter and will do some of the averaging that NMR does. And that's really nice because Gaussian doesn't really do that.
I have a question for Laurie.
Yeah.
Hi. I've always been fascinated that the second row, or whatever we call it, the silicons and such, and phosphorus are so much different than the first. And what do you do with this fact that pH3 has a nearly 90-degree angle? I'm just wondering how you handle that with your students.
Yeah, it's interesting, right? Because when they draw the structure, remembering what they know from Gen Chem, that's not the structure they draw, right? And so we calculate several different structures and look at where the energy is, and then what's happening with the electron density, and they're all very surprised, right? And then later on we talk about it further in class. It's the first couple of days of inorganic, I'm reviewing Gen Chem, but kind of saying, well, we used a model in Gen Chem, and this class is going to be about breaking our model. And so this is a really good example of that.
Yeah, I think that's just terrific. I remember when I was an undergrad, Bill Goddard, I got to have as a professor, and he just sort of beat this into us that carbon, nitrogen, oxygen, and fluorine are just unique. You cannot extrapolate. Everything that we teach about hybridization pretty much is based on these few elements. And I guess I've been an inorganic chemist wannabe for all these years, just because you guys have so much fun with doing exactly that. It was just breaking all these rules and blowing people's brains. The reality
I love it when students, because they've had sort of Gen Chem, the organic sequence, and a lot of them are biochem majors. So it's been that is what chemistry is in their head. And then you show them like, oh, but is it always that way? And you can see some of them get really like excited about that. Like, I don't know.
Yeah, Bob, you should check out. Bob, I just want to say, so our last SLiTHEr, which is, you can watch all the recordings of all our SLiTHER. So it was said in the chat, and I put the link.
Yeah.
It was on why that, and doing it qualitatively, just Lewis structures and simple what actual hybridization is. Ulrich Feckel did a great job showing it. And so he gave his kind of practice lecture, and you can watch the YouTube link and see how he explains it on like the board. And then the computational stuff backs that up to get the 90-degree angles. And that it's ST hybridization, not SP anything. So that was a really cool thing. And so you can watch the video. It's about like an hour long.
I wonder if we really have to wait till junior year for a few inorganic chemists to learn that lesson. Why do we hide it in the first year? Or maybe you don't. Maybe when you teach first year chemistry, you say, but.
Yeah, this is something we've all been discussing in terms of like Gen Chem books and stuff too, right? Teaching about these models that are pretty wrong, and when you get to some of this stuff.
But that's why we do it though, because the books have it all wrong. Yeah. And until the books change, which will never happen, right? Because we're all academics. So it's yeah. I have tried. And Nancy, I see you there. I have taught Nancy's rant to first year students. Nancy wrote a very well tongue-in-cheek rant about Pauling and everyone else, and I tried to teach that to my first year students, and they just they're like, they had no idea what was. I had to apologize to them. I had to apologize to my other faculty because I'd ruined their lives because everything that they'd learned was a lie, and which is a good lesson, but I don't recommend doing that to first year students in a team taught course. If it's only you, that's one thing.
Not for tenure.
So the Macmillan Achieve interactive book that's come out, that's sort of that Macmillan is pushing right now. It does not sp3d2 hybridize. It gets up to sp3 and then it just stops and says, and then there's other stuff.
The periodic table.
I guess that's better.
That's a start. Yeah. Is there any other thoughts on CompChem, or if you tried stuff, or yeah?
So I actually adapted, I think, a version of that manganese experiment last year when we were all virtual. So I kind of dropped it in the chat, but we didn't use WebMO or a cluster. I had students essentially run it on their own computers, which took a little bit of trial and error because, running these calculations with Orca input files, right, you have to use the command line and all that, which takes some learning. But that is kind of a nice alternative, right? Or at least it kind of highlights the time that it can take to do these calculations, because it's not just like, oh, I have this idea, I'm going to press a button and get a result, right? Even for really simple compounds, it'll take 20 or 25 minutes on just a normal everyday computer. And then, we also learned some of the problems of designing our own ligands and putting them on there. And there was one that I think someone even just had like triethylphosphine they put on it. And in the course of the optimization, the phosphine, you can watch it like separate and then move further and further apart because dissociation is the lowest energy state. But yeah, so having them kind of run it on their own is interesting. I added a few extra points on there where I had them essentially at each step of the optimization get the metal carbon bond length and the carbon oxygen bond length and plot those versus the energy, the single point energy for the optimization step. So you can see like the energy decreasing and some bonds shorten and some elongate. And that was kind of an interesting addendum to it. But But yeah, I think the interface part is always kind of the challenge with these, is going from, I have an idea and I want to model this, to getting the results is really tricky. So in the chat, we talked a little bit about Avogadro, which is completely free, that allows you to kind of build molecules, and it will actually generate these input files that then you can run, which is handy. It can also visualize a lot of the data on the back end. So that's what we used to kind of get through that. There's another one that one of my colleagues is really invested in that I like. So instead of using Orca, it's called SLiThEr. And they actually have a suite of labs that are experiments that are developed for educational purposes. The thing that I really like about SLiThEr is it's Pythonic, which means you can actually run it in essentially a Python script, which again is another barrier to figuring out how to do, but it's a little bit easier to deploy, a Jupyter notebook that can run Python scripts than to install these giant computational packages. And then the other advantage of that is then you can process the data right in the same place that you run it, right? So you can run it and then you can extract, final energies and these trajectories and all that kind of stuff all in one place, which is nice. But yeah, that's, I think, the biggest challenge for employing any of these things in an educational setting is that gap between idea and execution, right? Once you get the data, I think most people are fine with like trying to think about what the data is and how to kind of work with it. But getting it installed and running is hard, right? So that's definitely the kind of big barrier to entry there.
Yeah. Even with like Gaussian and stuff, like we don't have Webmo, I'm working on getting it, but like we only have a certain number of seats of Gauss-View and so I did have students like who are external, and they could access our servers off campus, but they could so they would use Avogadro off campus because they didn't have Gauss-View, but they could do similar things, like look at the results, work on things, and then do the rest in the the command line within the server, VI and stuff. So we kind of did that workaround in terms of trying to figure out like piecing things together when everybody's remote and stuff. And there are ways of doing it, but yeah, it just takes a lot of learning. The learning curve is not simple.
But unlike teaching a lab where the learning curve is also high, you can't really hurt yourself. You could probably get carpal tunnel syndrome, right? So the students are always scared to push buttons in the lab, right? Until they reach that threshold, and then they're like, oh yeah, I rebooted the NMR. Like, you what? and whereas with Comp Chem, you're like, no, you can push all the buttons you want, do whatever you want, and it'll work. And if it doesn't work, then let's figure it out. I think it's a way to sort of let them explore with really no risk, right? If they see smoke coming out of their hard drive, maybe they should slow down. But
there's a really interesting paper, and it's like a DFT, the devil's in the details. I can't remember where it was published, but I think I've posted on the Discord a time or two. And what I liked about it is it's written as like an introduction to basis sets and like the nuts and bolts of processing computational data. But the supporting info, there's actually two supporting infos. One is written as a workbook, telling you essentially the things to process and think about and questions to answer. And then there's a version of the supporting info that essentially has all those answers to it. So you can kind of read the paper and follow along. And then one of the SIs you can have open next to it that has, try running this benchmark with these 5 basis sets and figure out which ones, gets you closest to the experimental data. And it was really interesting to kind of go through. Again, it starts on the opposite end of that gap I told you. It assumes you know how to run and get all this data. It's purely about processing the data off the back end, but it's another interesting kind of starting point.
Bob, did you have your hand up?
Well, I was thinking, can't what they do is submit a job that's an infinite time job or something like that? I mean, it's not the same as unplugging the NMR, but it could have some effects.
Yeah, they certainly can. I mean, when I have my students do this, I'm keeping an eye on the administrator interface, right? And
this is the WebMO.
The WebMO, right? Okay. But if whatever I could do it from Gaussian from the command line too, and just see what processor's taking forever. I've actually capped the number of cycle processor hours that I give the kind of education chem student group, so that it doesn't interfere with other people's calculations. it depends on how you'd set up your cluster and who else is using it. And actually the computer science people are sort of in charge of mine, and they have ideas about, how to best do the kind of load leveling and stuff. So when that happens, when a student does that, it's often because they've submitted something that I know is going to take too long, but they don't, right? And so they dream up this like phosphine ligand with like, the biggest, floppiest things, which is just, it's going to take weeks, right, to get a minimum. I mean, they're going to find transition state, and it's just going to take, and I want it to take like, a day, an hour, right? And so I'm like, okay, well, I see what you're going for here. What's a smaller version? And we talk about model chemistry and how, all the time people are, using methyls instead of, some T-butyl neopentyl thing, or they're, using a chlorine instead of a, aromatic group with a electron, with a group on it. So we talk about that, and I'm like, well, so do you want to redo your calculation? Because this one's not going to finish before the due date. And they usually agree.
Yeah, speaking of we had the comp sci people running ours, and they put some program on it or something that like suddenly made all jobs just not run. It took us forever to figure out. They were like started, but they just didn't actually cycle into the proper thing, or just sitting there spinning their wheels, and it took forever. But it's the same thing with like my research students too that have done this. They're like, okay, how long is this going to take? To start small and then work your way up, right, and see how long things are going to take.
It'd be interesting to have a little utility that actually could give you a hint about that. Push a little button on Webmo and say, well, this is going to take 3 days probably.
Expected calculation time.
Yeah, but the thing that's always is that you see some papers will report those, but it's relative because every single server cluster is different, right? In terms of its number of nodes, RAM, megahertz, gigahertz, whatever, and also then it depends on the basis set and functional too. So like,
it depends on how good their guess is, right? Yeah. And so this is actually usually the student's first mistake, right? Is they draw something and then the Webmo interface does have an optimized, but it's really good for organics, but it's not good for inorganics. And so if you're not careful of how you do it, or you're not paying attention to the point group, you end up with something that's like all kinds of not octahedral, right? And it's going to fail. It's not even going to go. And so helping students recognize that kind of garbage in is garbage out. And when they need to, for example, load in a sample, octahedral complex, and those exist in Webmo, but you could do it in Avogadro or whatever, right?
Or Gaussian.
Here are some already optimized ones. So instead of drawing ferrocene from scratch, which is real hard for a student, right? Here's a metallocene, change the metal, right? Here's a metallocene, add a methyl group. That's a much easier task than draw. So that's helping students figure out a workflow that lets them not submit stupid stuff is also useful for them.
I wanted to say something else about getting help as well. And when I first started teaching Comp Chem, I would just call up Lori. So I'm going to throw her under the bus right now. So call Lori when you have questions. She was really helpful and explained to me why I can't make things be 180 degrees and things I never would have guessed in a million years. And then when I started using it in research, I'll throw another person under the bus who's not here, and that is a friend of Viper, Richard Lord, who's at GVSU and who is a computational chemist who knows so much. And Richard has been super helpful with DFT questions and all the weird things I was trying to do. So you need to have a buddy to call. And then also on top of that, there are these regional groups. And so, for example, in the Midwest, we have MU3C, and so that's Bob. Bob, that's something that you could be part of, and or maybe you already are. I don't know. And so it's just a bunch of Midwestern people at small colleges that do computational work, and the clusters sit at Hope College, and so we maintain the clusters and stuff. But people in MU3C do a lot of their if they don't have their own computational resource, they do it off on our clusters. And then they also have an annual undergraduate research conference virtual conference that they've been doing for a long time. And so those groups, and then what's the one out east, Mercury or whatever, those groups are really, really helpful.
There are even some, there's some national sites too, kind of run out of national labs, I think, that will also, you submit a request for time, but a lot of them even have Gaussian and other of these packages installed, and you can use their clusters. So not having your cluster is fine. And you can do, like some of the people in the chat said, you can do these on workstations too, though they can get slow. So if you're going to have students do them on their individual computers, you got to be kind of careful about what you have them do.
And to go follow up on that, I've spent this whole semester trying to set up a server in my department. So I got I found an old server that we had sitting around being unused. It had like something like 64 cores, and it was being literally unused. It was dust. So I spent the summer buying RAM and uploading everything, and all of our students have iPads. So we're setting it up for the spring where we're going to let all of our students hit the server through the Webmo app on their iPads and do calculations to sort of go take away some of that sort of, entry level sort of issue, right? Now the only thing that I have to do is actually learn how to do computational chemistry. So if I can do that, like, I'll be in really good shape, right? Because I've got the computer and all the software is on order, right? Now I just have to learn how to actually like go and set things up right, so I don't put in all the garbage, Lori, right? Because that will be me.
Well, there you go. You've got Lori to ask questions, and all the stuff.
The good thing is most of these packages, if you're really, really far off, they'll just like stop and they'll be like, yeah, try again. Only they just stop. So
yeah, they kind of break. So WebMO, we use WebMO in our Gen Chem class, but going back to Avogadro a little bit, one of the really fancy things that it has that's nice is it has like a super low level optimization or energy optimization script, whatever it is that runs in the background. And so that's at least gets rid of some of those, really nasty geometries. A lot of things will kind of lock into a pseudo octahedral thing. It essentially goes back to giving you a good first guess, which I totally agree is the number one hardest thing, right? If you have a really bad drawing, a lot of time, like, your ligands will get locked on each other and then they won't rotate where you want them to be. And so using some of those tools to kind of make your initial guess better dramatically improves your computational time.
You know what they're using for that? Do you know if it's UFF?
I'm not sure. I think it's like a simple like force field model. Like there's no MOs, nothing on the back end. It's literally just kind of getting atoms in a reasonable location.
Yeah, there is a force field like MMFF95. There's one called UFF, which is for transition metals, and supposedly works well. I haven't had super success with it. Again, try to do a little 2D drawing of an organometallic complex, and it kind of
I'd be really curious about that, because there was a paper that came out about like how horrible PM7 was with transition metals, where they were trying to even like model the metal and then model everything else with semi-empirical, which is another lower level, which kind of between force fields and DFT, and it was all wrong. But yeah, those I'd be curious about, because I always have steered away from all of those things because of how they treat metals. But yeah, I'd be curious. Cool.
We really need a 2D to 3D drawing utility for inorganic chemistry, don't you think? Raise your hand if you'd like to have a 2D to 3D drawing utility.
Yep.
Can't we come up with that, someone here?
Yeah.
I'd also be in for like a
what?
Telepathic, just think about the molecule. I like that.
Oh, yeah.
Or
so
even
it was
like you could give it a point group and have it comply, right?
Yeah. In the chat, there's a evaluation on today's SLiTHER. Please, be sure to fill that out. Sarah, do you want to say anything?
Yeah, I'd also ask if there's any other ideas for future SLiTHERs you have. So we're going to keep doing these in 2022. So if you have an idea for something you want to present or want to try to get someone else to do for you, we'd love to hear about that. So
Yeah, anything related to teaching, research, students, inorganic chemistry, inorganic related adjacent chemistry.
yeah, if you think it's interesting, we will too, probably. So yeah. Anyway, this has been a really good, at least a start to discussion. I'm sure we can keep going on Discord and other channels that we have to talk. So